There we go. And well, my name is Antonio Rodriguez. Thanks for having me. And by the way, I, like a politician, if I see a microphone that is over there, I'll just take it and grab it and start talking. So it wasn't too much of an effort in which you send that email, hey, I need a speaker, and I think you measure it, it must have been like 5 minutes before my answer came, hey, I don't know what, but I'll talk. Anyway, so how to detect Parkinson tremors using ML and microwatts? A lot of my search, I've been working with very power constrained devices for a lot of times. Whenever you need to depend only on the battery, and that battery has to last at least a year, then you have a battery constrained device. First, some disclaimers. First, this is not a medical claim. So if there's a lawyer over here that was thinking, hey, I have someone to sue, disclaimer, not a medical claim. It is a simulation. I'm hoping not to offend anyone. I'm going to simulate that I'm having a Parkinson tremor. I don't have Parkinson myself, but I'm going to simulate it. I hope I don't offend anyone by this. And lastly, this is an oversimplification of the whole procedure of getting something to work. One of the things that I've been reading is that when you start with machine learning or AI, and you're a software engineer, your focus shift from when it was 100% coding before, now it's like 10 to 15% coding, and the rest of the time is just playing with the data and training and testing and doing it again until you get it right. So it's a lot of that. We're going to do everything over here right now. But it's, again, if I give you the wrong impression that this is straightforward and easy, don't. A lot of the parameters, I already played with them. I know which one work, which parameter do not. So here we go. So we're going to be talking about many disciplines. I think a lot of you are going to be doing fact checking. Hey, you didn't say it correctly. It should have been said like this, or the correct name is like this. Everything's new. And besides, I have the microphone, so I'll just tell some little lies now and then. First, we're going to be doing some stochastic label data gathering. I already did that. I have my sets over here already labeled. It would have not been enough time to do the data gathering. We're going to do signal selection and conditioning, feature extraction, the selection of the ML algorithm. I'll talk about it. I already selected it. Do the training, implementation of inference, detection of labels, and testing. So, how do I get here? Why do I like this? I've been working for a lot of times with again devices that are power constrained and connection constrained. Connection constraint is you don't have a lot of bandwidth and you're not always connected. Sometimes you're just offline. And you depend either on a con battery, a couple, or just one AAA, etc. And that's what the only thing that you have. Now, everything that has been happening lately has brought us to this situation. MEMS technology, micro machining, has been advancing a lot. Like, for example, IMUs are more sensible now. They're smaller. They have more precision. They started coming with a machine learning course inside the same device. Something very similar to what is happening, to what happens in our body. I mean, in our body, the neurons are not only in the head. We have neurons all over our body, and all of them have different functions. For example, some neurons that I'm very familiar with right now is neurons that we have in our ears to take away the noise and just and filter the voice. I know a lot about them because I've been hard of hearing most of my life. These things are for hearing, and these are great. They work better than my regular hearing aids for beam focus, etc. And it is neuron doing that function over here. It was inevitable that we were going to go into the Internet of Things would become also intelligent things because of all the miniaturization that has been happening. Because again, it had to be disconnected, low power. Something very important that started to happen is not very down to the microwatts level, but it was Google TensorFlow Lite implementation, in which they really trimmed things down in order to put it in a microcontroller. On the TinyML meetup, I went, when was it? December? The last one? November, December? So I was thinking about doing something like that because I was already looking into TensorFlow Lite. I saw that you were going to have some demos, so I went rushing over there and saw some fabulous presentations as well. One of them that I liked a lot was the Qualcomm, in which there's a new Qualcomm camera in which the machine learning core it's already embedded into the ISP, into the chip that processes the video. So this is important because you don't have to go all the way to the cloud to do the inference and come back and make a decision. You just make it right there. So the new thing is now, okay, now it's clear. We have training in the cloud or in the computer, as I'm going to show right now, and execution on the device. But it is also important. Okay, but what kind of execution? So we've come a long way. It seemed like only yesterday when the whole artificial intelligence thing started, but we're overflow with different algorithms right now. Most of all, it's like the latest flavor, or this algorithm is good for this is good for that. One of the important parts of all this is TensorFlow showed the RNN, recursive neural network, recurrent neural network. Why that was important? Because they figure out to really train it, trim it, and put it down into code that could be easily executed. That's the nice thing about that. So you can do it. The important parts are you can do it offline again. One of the things where you started seeing it work, it was in the predictive response in Gmail, like you told, it says, why don't you answer this? So that's the machine learning working right there. One of the important things about all this coming together is also the new ARM microcontrollers. The new M4s, the M33s, M7, they come with three basic things that are very important for machine learning. One of them is DSP extensions. DSP extensions are very important for signal conditioning. Most of what you're going to be doing with little devices is conditioning the signal, as we're going to show here. So you need hardware to help you in that. If you're just going to be doing the math without that, it's going to take a long time. The other one is the multiply, add, accumulate. That's also important for the calculation, and single instruction, multiple data. That's important also for voice, video, etc., etc. So all that it's coming. Now, part of the problem, I started my quest into trying to detect a Parkinson tremor with TensorFlow, only to fail miserably. Two reasons for this. First, it is still heavy for this. If you really want to be low power, it is very heavy, and it's only in C++, which for the hardware community, being only in C++ is a problem. If, like for example, we have in Nordic, it worked on the particle that come with Nordic, it worked, but only if you had Arduino, which is already C++, or Embed, which is already C++, or Particle, they did their own stack, which is already C++. But if you want to go deeper into developing a product that you're going to deliver to the public, not a proof of concept, then you have to go with a regular SDKs, and SDKs are not in C++. So that is a problem. It still takes, I did some testing, the inference time was 6 milliseconds, which is a lot in machine time. It was taking 4.6K RAM, which again, it's a lot on battery terms. I mean, for proof of concept, it works, but we still have to go deeper into that. And one thing I have to say in favor of the implementation of this is that Nordic chip, the actual M4s, they don't have DSP extensions or Mac or SIMD, so everything has to run extended. It's like trying to do floating point without a floating point coprocessor. So I found an IMU which had a machine learning core implementation, the same as Qualcomm, inside the IMU. They did something not very powerful, but powerful enough for most implementation for gesturing. And the algorithm that they decided to use is a decision tree algorithm. You're going to see a little later on why it was very smart to use that one. They're using 0.55 milliamps at 1.8, so 990 microwatts. Most of it this is in high performance, the IMU. If you read the specs of any IMU, that's what they consume, just the IMU without the machine learning core. About 5% or less is the machine learning core. So they kind of piggybacked in something that was already consuming power. If let's say that I wanted to do that with an external IMU, because you can also do over here the IMU and then take it externally and use. So we would be talking at least 3.3 milliamps extra on top of the 0.55 milliamps that we already have. So we're talking at least 5-fold, 6-fold of power. The way they're doing it is in the little chip, which is very small, by the way. It's 2.5 by 3 millimeters. They have the input, which is the accelerometer and the gyro. They have this feed the machine learning core, and the machine learning core makes an output. Okay, and without further ado, we're going to start our demo. So this little device has the accelerometer and gyro inside. You can see over here, it's connected already. You can see when I'm moving it. This is the gyroscope, this is the accelerometer. You can see each of the 3 axes. So when I'm doing this, you can see that the X is moving, or the Y for the gyro, or over here we're talking about Z in the acceleration. And since I don't know if what we're going to do is going to work, I have it working right now. So before we try to do something that will maybe not work, I will show it to you working. So this is the device that is inside here. If you see, I have the accelerometer and the gyro. It's a sensor box. It has all kind of different sensors. I have it the accelerometer at 26 ODR, and which is basically the sampling frequency, the output data rate. And the gyro, it's also at 26, which is great for, and it's high performance, which is great for gesturing. It's good enough, and it will capture everything that we need. I placed the gyro, even though the gyro can go all the way to 4,000 degrees per second. I place it at 245 to have better resolutions. If you see over here, it really doesn't go beyond that. And as well on the accelerometer, the full scale is 2G, because you don't need more. Okay, so I have a logic analyzer. Basically, this is already trained, but I'm going to retrain it later. This is already trained, and over here, every time that it detects the 2 labels that I created, I created 2 labels: normal, which is just regular movement, and tremor, which is a tremor is detected. A little history here. We finished a medical device last year for Parkinson stimulation. So whenever a patient starts having a tremor, it starts stimulation, and it stops the tremor. So it's basically 4 wearables, 2 here on the wrist and on the legs. And But after we finished it, I kept thinking, well, it's going to be a little awkward if you're starting having a tremor, that you have to take your phone out and start the app and everything. It should detect it automatically. So that's when I started to look, okay, how can I make this work? My initial thought was to use the same microcontroller and the same IMU that I was using already on the wearables. But that was the whole TensorFlow thing, and I already said that story. So again, I have two levels over here, and over here we're looking at in the first one. You see a check on 0, 1. Do you see it over here? This one, basically, and this is the logic analyzer, because when it detects the tremor, it's going to generate an interrupt, so it wakes up the MCU, and the MCU goes and it's not doing that of course right now, but it generates the interrupt, and the idea is that it starts the stimulation. So I'm going to start. And there, see how it changed to position number 4, and it generated an interrupt. And then when I stopped, it returns to position number 1, which is normal. So thank you for the applause. Okay, so now that it worked, now let's try to make it work, and if it fails, thank you for the applause. Okay. So I'm going to first get rid of this. This is how we do it. I am using one of the nice things that I liked about this IMU is that it came with tools for the whole training and everything. So they're not very advanced as they would be for Google, but they do the work, and they do it really well. And by the way, I've been working with IMUs for several years, and this is nice. Having the ability for, if anyone has worked with IMUs, having the ability to, let me show you something here. Okay, here I'm going to do this offline because they still do not detect their own IMU for this sense. For the Unico is their tool that they use for training. So, but if it were connected, one of the nice things is that you have access to all the registers, you can change them. I like it a lot. In this one, we're going to go to the machine learning core, and we're going to start the training. First, we're going to browse for our data. I already have it here. I have normal. So there we have the data, and I'm going to label it as normal. So there. And this is upward. Tremor. By the way, this other tool, the one in which you're looking at the gyro, that's the one that I used for capturing this data. So tremor, and then we have our two labels, and we start the configuration. So So first, that's the IMU that I'm using. It asked me for the ODR, is 26 Hertz, as you saw before. I'm going to do accelerometer and gyroscope. 2G. The accelerometer ODR. The first one was the machine learning core ODR, which I'm placing at the same one as the accelerometer and gyro. So the accelerometer is at 26 Hertz. As I said, I'm going to place it at 250 DPS. The gyro is 26 Hertz. I'm just going to do one decision tree. I'm keeping it simple. My window is going to be 52 samples. If you saw there was a gap of 2 seconds before it actually detected that, because that's the window that I'm giving the machine learning core of data to make a decision. And then we start with the filters. As you saw, so this is one thing. If you look over here, before we go into that, we were talking about signal conditioning. One of the important parts about choosing your features is, okay, wild guess, which are your best features? You have to select which features are the ones that are going to make sense to detect whatever you're looking for. So that's the reason it's important to have all these. We can also have, let me execute here. There's a Fourier over here, which I can place at 32 and take the DC out. So if you see, if you're having a tremor, you kind of look, the frequency, it's about 4 Hertz. So in that sense, you can start saying, oh, maybe if I do a bandpass filter at around 4 Hertz, I will have better precision and I'm going to be helping my algorithm. Because again, what we're trying is to keep it as simple as possible over here to detect the features. So you have here also, if we go over here, you can see that the red one, which is the gyro X, is the one that is having the most peak to peak. So you would say, yeah, that's the one that has the most energy as well for what I'm trying to detect. On the upper one, on the acceleration, you don't see a lot of peak to peak over there. So you're saying, or maybe the gyroscope data has more information about what I'm looking for than the acceleration itself. So this is how you start kind of looking, okay, what am I going to use for my features? So I come back to my here, and I have several filters that I can use. I can do high pass on the acceleration, X, Y, and Z, or high pass on the acceleration, the norm, or high pass on the acceleration. Can you look at that? I don't know if you if you're able to.
You've got a monitor over here that helps.
High pass on the acceleration on the norm square, or a band pass on the acceleration. So you have several filters that you can choose from. There's even some filters that you can define yourself. In this case, to show it, I'm going to do a band pass. on the acceleration. Oh no, I'll just pass the acceleration by itself. I'll go directly to the gyro. So I'm going to do a band pass on the gyro. X, Y, and Z, because I noticed the X is kind of doing a lot of stuff. So it's asking me for the coefficients now. Remember that we talked about 4 hertz? So we go over here, and you can use Matlab, you can use Python, you can use, I like this one because it's free, and I'm from Monterey. Only my friend from Mexico understood that. And so we're going to do a filter over here. It's already pre-selected, so let me connect. Okay, I'm going to, the central frequency is going to be 4, and I'm going to do it with a bandwidth of 0.4 hertz, if you will. But I'm just choosing something. So I run it, and
You got 2 dots.
okay, you're not the only one that are not being able to read. Okay, save it and run. Okay, so we have our filter, very nice. I mean, it's a Butterworth second order, so don't expect too much from it. But it works, and it's giving me the coefficients here. So I start putting the coefficients first, the A. Then we need the A3. In case you're wondering, the formula, this is the filter that we're implementing, and this is the formula of the filter. So that one, now A3, and finally there's a normalization, because we have a 1, 0, minus 1 here on B, which can be sent to the gain, which is what we're going to use. And we're going to place it as gain. Okay, so since it already worked, I'm just going to define that one. Okay, so now it comes the fun part. So it starts giving me all the different variables about what I want to select as features. I already selected just one filter. It's going to show it to me. And this would be the part in which these are the formulas of the different features that we can select. We have mean, variance, energy, peak to peak, zero crossing, etc. Different things, including the filters. These are the formula for every one of them. So we start selecting, okay, I won't bother, but just the mean square of the acceleration. I'm also going to use the filter that I selected on X. Just let me make sure, double sure it was X. Yeah, it is X. X, and one important thing over here, it's X. We're talking about the mean. So if you leave it sign, the mean is going to be 0 since it's oscillating. So we have to we don't want it sign. If it had a DC bias, then we could use the sign, but in this case it doesn't help. And I'm just going to do the same with the variance. Maybe it'll work. I'm going to select on the variance also. I'm going to put a 3 over here. Part of the nice thing, the same as with TensorFlow like, is that if you're not sure about a feature, put it in. Because when you do the pruning, it's going to be taken out. If it's non-relevant, it's going to be taken out when the training is happening. So I'm just placing those in. I'm going to put again over here the energy of the acceleration on the norm square. I'm going to place both the 3 of them of the gyro, not sign. And finally the peak to peak, because it's really visible, the peak to peak, so I want those. And why not also the gyro square. Okay, so when you select all your features, the next thing that you do is that it's going to make a file ready to be sent to statistical analysis. I'm going to call it ACL since this is the room which we're on. It generated it. Now over here, if it is normal, I want to give me a 1. If it is a tremor, a 4. Those were the places that you saw on the machine learning core of the results. So now it's asking me for the decision tree. So it's now time to launch our statistical tool, which some of you may be familiar, which is Weka, or Weka. So in this, we're going to go into Explorer, and we're going to select a filter well, first we're going to open the file that we just generated. It was in big USB. ACL. Okay, so over here we won't do it right now, but if you want to visualize all the relationship between different features, there you have it, the different colors to quickly see them. And also to kind of visualize which ones are relevant and which are not. There's especially over here a filter, which is a C4, which is called J48. This one especially makes the tree that we need. And now it run. It's telling me that it has a 91.95 precision. We have the confusion matrix over here. It's not that confused. And these are the features that we placed as input. And this is the tree that is generating. And we're going to create a file with that tree. Which is called ACL tree. And we're going to place internally the tree. Now, if you can read this, you can see how easy it'll be for any hardware core to read it or to execute it. It's just a decision tree, which the first one is if the absolute of the filter that we created, so we were right that the gyro has important information. If the value on that is less than blah blah blah, then it's normal. If it's more than that, then it goes into the next one, which is analyzing the peak-to-peak absolute on the filter again, on gyro Z. And if it has certain value, and if the energy of the norm square is below certain value, it's a tremor. If it's not, it's normal. If that was not, then it was normal, etc., etc. So a lot of times it's really a big tree. This was a small tree. We don't know if it's going to work anyway. I've seen someone that it's it cannot be that easy, the decision, and then it's not easy. If you're familiar with overfeeding, yeah, if it's too easy, most likely you're overfeeding. So now we're going to come again to the one that is making the this one, and we're going to feed that tree. So we browse and we blue and so ACL tree, okay, it's in. There's some other tools that we won't use right now. So now it's going to generate exactly the file that goes into the IMU. For that, we're going to call it ACL. And bingo is created. So now we go back to the one that is doing the, where is it? I have too many windows open. Okay, so we're going to open the machine learning tool again, and we're going to get the file that we just created, ACL, and it's downloading it here, and there. It says that I'm normal, I'm moving, etc., but I start having a tremor, and come on, don't let me down. And
You reset it all?
hold on. For some reason, this is.
Move now.
acting weirdly. I'm going to stop, start. Yeah, there.
Awesome.
Did you see it? I mean, it's most likely that another implementation that I did on my own lab was better fitted for this, but this one also did work.
Show it again.
How are we in time?
Uh,
We're done. Okay.
yeah, 8:02.
Okay, so if you want at the end, I have another one for showing in which speed the fan is on, based on the FFT analysis, well, on the learning of the different vibration that is generating at the different speed that it has. And it says it's off, it's low, it's medium, it's high, etc. No, that's the one that I was going to show, but we'll save it for later. Oh no, we'll save it for the tiny ML. Okay, some limitations. Of course, not everything is perfect with very low power. So the maximum ODR is 104. So if you're trying to get something really fast, like what you need in industrial environment, you do need the power. If you're going to frequencies beyond 104 hertz, it doesn't have a sliding window. It's just a fixed window, one after the other after the other. Why is that important? Because let's say you're doing gesturing and you're selecting A or B or C. If the windows happen to be in the middle of you doing the C, then it won't detect it because you just slide a window in the middle of the gesturing happening. So it doesn't have a sliding window, and it only has IIR second order. You know, if you want a really nice cut frequency, you have to go to higher orders. It doesn't have FFT, so there's not a lot of tools, but for gesturing, for regular gesturing, most of all, when the gesturing is repeatable, it works perfectly. Like for example, for jumping, step, going to the gym, what I just showed, everything that is repeatable is perfect because the window will fit right into what you're doing and will detect it. Thank you very much.